So we're back. We're just talking about unit vectors, and I was rushing a little bit at the end, so I want to go more closely and a little more thoroughly into what we did here. So for this, we determined that the unit vector for the vector v, which is 2, 2, is by definition the vector divided by its norm, which is 1 over 2 the square root of 2, because the norm of v is 2 times the square root of 2. This is a scalar, so we can bring it inside the bracket notation. Bam, bam, and we get 2 divided by 2 times the square root of 2, and comma 2 times the 2 divided by 2 times the square root of 2. This is 1 over the square root of 2, 1 over the square root of 2. This is what our normed vector is, right? Or we're claiming. Is it really a norm? Well, I did it. I took the norm of this. We squared this off. Indeed, we get 1. And then we've said, okay, so its length is 1. Is it really in the same direction? And we figured out the direction of this. The direction of any vector in 2 dimensions is going to be the arctangent of y divided by x, because that's how we figure out in this picture what the angle is. And assuming that x is not 0, of course, you should always say that. And 2 divided by 2 is 1. The arctangent of 1 is 45 degrees, which is pi over 4. Now we did the same thing here, and this is where I was rushing and I got a little sloppy, and I want to make sure this is clear. This is our normed vector. This is the x component. This is the y. 1 over the square root of 2 divided by 1 over the square root of 2 is in fact 1. The arctangent of 1 is pi over 4. So this is the same as this. And so what is it? What does it really mean? Why is there a unit vector? What good is it? Who cares? Well, this is the unit vector. So if this drawing was right, and I guess I'll do this. This is... And the reason you want unit vectors is so you can manipulate your vectors easily. What if I wanted a vector that was in the same direction but 20 times as long? Well, what I would do is I would just do 20 times the unit vector, which is 1 over the square root of 2, 1 over the square root of 2. The 20 goes inside, but it's really easy to manipulate. Unit vectors are essential. They're pretty groovy. And now when I said that unit vectors don't have a standard notation when you're computing them this way, I guess this is it. However, they really do. And here is what you will love and perhaps be slightly driven mad by, because the letter I is going to show up again, but it has nothing to do with the square root of -1 in general. So in 2 dimensions, the unit vectors for the x and y axis are usually given by this. This is called the I-axis, which is really the x-axis, but I is the unit vector, and I'll show you what I mean. This is the x-axis, and here is j, is the y-axis. And here's what I mean. Basically, suppose that u is a vector is a, b. This unit vector, I, is really, so what does I equal? I is equal to 1 and 0, okay? J is equal to 0 and 1. You'll notice so I is 1, here is I. Let me show you I. So this little chunk right here is I, but it's at 1. I won't write the I there. And I need more colors. I lost my yellow. What do we got? Blue, I suppose. No, I got blue up there. Red will do. So here is J, right? And it's 1 length. It should be clear that the norm of these are each just 1, because the norm of I is going to be 1 squared plus 0 squared square root, which is just 1, and the norm of J will be 0 squared plus 1 squared square root is 1. So the norm of each of these is 1. And here's the deal. All the vectors in the plane, this is going to be your vector AB. This is the point AB in the plane. This is U, which is AB. Here's what's really cool about vectors in the plane everywhere. And why we're doing things this way. We can write this vector u as in terms of I and j. I and j are what's called a basis for this space. Every vector that can show up in this space, we can write like this. This is u is equal to a, okay, so let me do it like this. ai plus bj. And it just occurred to me having bj there wasn't the smartest thing I did all day. However, it happens. It's not my fault. Let's see what this is. This is a times 1, 0 plus b times 0, 1. We already said a and b are scalars. We know they multiply inside. This is a 0 plus b times 0 is still 0, b. But remember how these add. They add component-wise. This is a plus 0 and 0 plus b. This is a b. This forms a basis for this two-dimensional vector space. Incidentally, when you go to 3 dimensions, it changes. And like I said, I'm so sorry that the book we have in this course isn't rigorous enough to go to 3 dimensions, but I'll show you anyway. In 3 dimensions, it's like this, and we have k, which is 0, 0, 1. And all of these are unit vectors, and in 3 dimensions, these 3 unit vectors span the vector space. And the span means that any vector in here can be decomposed into these units. And this is tremendously useful because you have AB here, so that means that this is A times I here. This gives you tremendous amount of information, and this is B times J up here, all right? Totally, totally groovy. And remember, so, I'm so sorry. There's always so many symbols that we have. In this case, I does not equal the square root of -1. And if you end up going into electrical engineering, it's even more bizarre. In electrical engineering, J equals the square root of -1 because they use I for current or something like that. You just get used to your symbols in your context. Stay glued to your chair because some really exciting stuff is coming up. I wouldn't lie to you.